Welcome to the 32nd lecture of our combinatorics class. So last lecture, we ended with the following theorem, giving some necessary and sufficient condition for a graph to be bipartite in terms of the eigenvalues of its adjacency matrix. So the result is the following. If we have a graph with n vertices and adjacency matrix eigenvalues lambda 1 all the way to lambda n, then the fact that the graph is bipartite is equivalent to the spectrum of gamma being symmetric with respect to 0, which is also equivalent to the fact that for any odd natural number L, the sum of the L powers of the eigenvalues equals 0. So let me sketch a proof of this result. Now, the first part, 1 implies 2, we did it, we proved it last time. So we'll you can look up in the previous lecture for the details. Now the fact that 2 implies 3, it's pretty straightforward because if the spectrum of gamma is symmetric with respect to 0, then that means that we have an eigenvalue. Let's say if we have an eigenvalue theta, which is positive with multiplicity m, then that implies that eigenvalue minus theta will appear also with multiplicity m. So multiplicity. Tm. And now in the power, in the sum of the L powers in part 3 of the theorem, when you have the part involving theta to the L, you will get theta to the L plus theta to the L m times plus from the multiplicity plus minus theta to the L plus minus theta to the L also m times. And because m is odd, this will equal, because L is odd, this will give us 0. And so any contribution from a positive eigenvalue theta and it's negative will give us 0. And then the contribution from the eigenvalue 0, if it exists, will also be 0. So we get that the sum of the L powers of the eigenvalues must be 0. So that's 3. That's 2 implies 3. It's pretty easy to see actually that 1 and 3 are equivalent because if you remember the sum of the L powers of the eigenvalues here is the number of closed walks of length L in the graph. And so if the graph is bipartite, then there are no closed odd walks of any length. So that implies that this number of closed walk is 0. And that implies the equation in part 3. And similarly, if we assume part 3 being true, then that means that for any odd natural number L, the graph does not contain any closed walks of length L, and therefore the graph is bipartite. So again, this is a very nice example of results of spectral graph theory that on one side have a combinatorial property of the graph, in this case, the graph being bipartite, and this combinatorial property is actually equivalent to a linear algebraic property, which is the fact that the spectrum is symmetric with respect to 0. Okay. So now let's move on to one of the first application of eigenvalue methods in combinatorics, and this is related to what is called the degree diameter problem, or sometimes this is called the Moore problem. So there's a question on your homework about if we are given delta, let's say in our homework is greater or equal to think it was greater or equal to 3, and a diameter, say greater or equal to 1. And so we can change this. Let's just do delta greater or equal to 2. What is the maximum number of vertices of a delta regular graph with diameter d? Okay. And this question was asked by a mathematician named Moore in the 50s or 60s. And so this question was asked by so Moore proved the following upper bound. So you think, okay, I want to build such a graph with the largest number of vertices. What's the maximum number of vertices that you could have? You pick a vertex, let's say X. Then you consider its neighbors. And so you can think of listing these vertices by level. So here we're at the 0 neighborhood of 0 level of the graph, and we have 1 vertex. Now, because the graph we want is delta regular, then X has delta neighbors, so we have delta neighbors here. Then when we look at vertices at distance 2 from the graph, then what is the largest number of vertices that we can find there? Well, each vertex that's adjacent to X already has used 1 edge going to X. So it can have at most delta minus 1 edges going down. So the number of vertices going down has to be the number of vertices at distance 2 from the graph is at most delta times delta minus 1. And so we continue like this. We can go all the way. So this is, let me put here on this side, the levels. This is distance 1, distance 2, distance 0, distance 1, distance 2. If we go to distance d, which potentially could happen because the graph has diameter d, then what we have here is that you will have vertices here that are adjacent to the ones on the top. And what would be the maximum number of vertices that we can have there is delta times delta minus 1 to the power d minus 1. Okay, so what does it tell us? Well, this tells us that if gamma is a delta regular graph with diameter d, then the number of vertices in gamma, cardinality of gamma, is at most 1 plus delta times delta minus 1 plus delta times delta minus 1 to the power d minus 1. Okay, so this result, it's usually called the Moore bound graph theory. And so Moore derived this upper bound and asked the question, what graphs attain equality here in the Moore bound? So let's try with start with small cases. So let's see what happens if the diameter is 1. Well, if the diameter is 1, what do we have? We have a vertex that's adjacent to, so this is our vertex. We have 1 vertex there. And then you have delta vertices here, and that's, you know, that you don't have any vertices at distance 2 from X. But now, if we have two vertices here that are not adjacent, let's say a Y and a Z, then the distance between them would be 2. And so we want diameter 1. So that means, so diameter 1 forces everybody there to be adjacent. And that implies that the graph, there's only one graph actually with diameter 1 and maximum degree delta, and that's the complete graph on delta plus 1 vertices. So that's pretty easy. Now, what I'll do today in for the rest of the lecture, discuss the situation with diameter equals 2. So for diameter equals 2, we have kind of this picture. So we have pick a vertex. Okay, then at the distance 1, we have delta vertices, and distance 2. So we are asking for a graph that attains equality in the Moore bound. So here we must have the maximum number of vertices, which is delta times delta minus 1. So if we specialize the Moore bound for diameter 2, it says that if gamma is a delta regular graph with diameter 2, then the number of vertices in gamma should be less than or equal than 1 plus delta times delta minus 1. And if you unpack this expression, you get it's equal to delta squared plus 1. Okay. So now what we would like to do is to understand what happens if equality is attained here. So what can we say about such graph? And we are going to prove the following famous theorem in spectral graph theory, in graph theory and combinatorics, which is due to Hoffman, Hoffman, and Singleton from 1960. And it states the following result: if gamma is a delta regular graph with diameter 2 and delta squared plus 1 vertices, so the one attaining equality above, then delta must be 2, 3, 7, or 57. And we will discuss later. So this gives you a necessary condition for delta. So delta must be one of these values. And that doesn't mean that necessarily that you can construct such a graph, but I will show later that if delta equals 2, there's a unique such graph. Maybe I'll state here, delta equals 2, there's a unique graph attaining unique construction, and that's the cycle C5. When delta equals 3, also it's a unique graph with these properties, and that's the Peterson graph. When delta equals 7, Hoffman and Singleton construct in this paper in 1960, they construct a graph with this property being 7 regular graph with diameter 2 and 50 vertices. And this is now called the Hoffman-Singleton graph. And it's also unique. It's the only one graph with these properties. And when delta equals 57, nobody knows. If I have time, I'll tell you a little bit about that as well at the end of the lecture. Okay, so let's prove this result. Okay, so gamma delta regular, diameter 2, d squared plus 1 vertices, two, 3, 7, 57. Now, the proof goes in steps. So one, we take A to be the adjacency matrix. So it's a proof using the eigenvalues of the graph. So A is the adjacency matrix of gamma. And now because gamma is delta regular, implies that if we multiply A by the all one vector, we are going to get delta times the all one vector. So that implies that delta is an eigenvalue of A. Okay, so that's the first step. And actually, delta has multiplicity 1. And we proved this before, but I'll prove it here. And the way you prove that, you take an eigenvector for delta. So you say AU equals delta U. Let's say U is a non-zero eigenvector. And then we take, so if we write this for each entry, it means that for every J in the vertex set, delta times Uj equals the summation over I adjacent to J of Ui. And now, if you take J such that Uj is the maximum entry in all these eigenvector entries, we can always assume that this maximum is positive. If it's not, you multiply by -1 and you make it the maximum is positive. And then we have that delta for this Uj, delta Uj is the summation of all I adjacent to J of Ui, but this is less than or equal because Uj is the largest, is the summation over all I adjacent to J of Uj, which is delta times Uj. So equality must happen here, must happen there. And how can that be? Then, well, it must be that Ui equals Uj for every I adjacent to J. So what happens is you have a vertex J, and now so here at vertex J, you have the eigenvector entry Uj, and at all of its neighbors, the eigenvector entries are going to be Uj. And now you can repeat this argument at any of these neighbors. And so by repeating this argument, you can prove that U1, all the eigenvector entries are equal. U1 equals U2 equals Un. And that implies that the vector U is a multiple of the all one vector. And so that gives us the proof that delta has multiplicity 1. Okay. Now what the plan for the next part of the proof is to figure out the other eigenvalues of the graph. Now, how do we do that? Well, we use the information about the graph. So the graph, I claim that the graph gamma has no triangles. And why is that? Well, if the graph had a triangle, you have something like this, okay? So you have some triangle in the graph. And let's say you have other vertices coming down. Now, so you have a vertex X here. This vertex adjacent to X, this vertex Y, has two edges already used. So it has at most delta -2 vertices going down. Okay. And similarly for the other vertex Z, it also has at most delta -2. This other vertex, maybe it has here has at most delta -2. This one also has at most delta -2. This other vertex has at most delta -1. But now when you add up the number of vertices in the graph, what you get is that the number of vertices in the graph is at most 1, the vertex on the top, plus delta, the neighbors, plus you see here Y and this vertex Z have at most, so one of them has delta -2, the other one has delta -2, plus the rest of them could have maximum going down. So how many are left here? Those are delta minus 2 vertices there, and each of them could have delta minus 1. But if you do the calculation of this expression, you get something which is strictly less than delta squared plus 1. And that gives us a contradiction because we have that the number of vertices in gamma equals delta squared plus 1. So essentially, the graph has to be as stretched as possible to maximize this number of the number of vertices. So you cannot have this short cycle triangles. And similarly, gamma has no cycles of length 4 because the argument is similar. So let's say you have something like this, and let's say you have a cycle of C4. So you have vertex X, Y, and Z, and they meet here in W. Y and Z have another neighbor W. Then if this, again, this, if I look at the contribution from this vertex here, this is at most, delta minus 2. This one similarly is at most delta minus 2. Together, Y and Z contribute at most 2 delta minus 3. Other vertices could be fine. They could have, at most delta minus 1 vertices going down. And when you do the count now, we get that the number of vertices in gamma, which again is we know it's delta squared plus 1, is at most 1, which is the vertex X plus delta, its neighbors, plus Y and Z going down are contribute to most 2 delta minus 3, okay, plus the remaining vertices, they're delta minus 2 of them, they contribute to most delta minus 1. And when you do the calculation here, you get that this number, I think it gives us delta squared, which is again gives us a contradiction. So you cannot have triangles, you cannot have cycles of length 4. Okay, what else can you deduce? Well, we can use this information to actually say something about the adjacency matrix of the graph. And how do we do that? Well, we look just, we take the adjacency matrix square, and we look at the entry xy in it. So x and y are some vertices in the graph. Now, the easiest case to figure out what a square in a position x and y is if x equals y. So if x equals y, this counts the number of walks of length 2 from x to x. And such a walk of length 2 from x to x, it means you start at x, you go on an edge which contain x, and you come back on the same edge. And how many edges are containing x? They're delta of them. So that's easy. Now, if x is adjacent to y, what will this count be? This is, so you have a situation here where x is adjacent to y, and you're counting the number of walks of length 2 from x to y. So you go from x to some other vertex z, and you go to y. But such walks, the number of such walks is the same as the number of triangles that contains x and y. And we saw before that there are no triangles. So this number is going to be 0. What about if x is not adjacent to y? Well, in that situation, x is not adjacent to y. Because the graph has diameter 2, there must be a path of length 2 from x to y. So there must be some vertex z here, okay, from x to, such that z is adjacent to both x and y. Well, how many such z's are there? Where there is at least one, because the graph has diameter 2. But if there were 2 or more, if there was another w, then you see that that creates a cycle of length 4, and there are no cycles of length 4. Therefore, there must be exactly one path of length 2 from x to y. So that means that a square of xy equals 1. Okay. Now, what does this give us? So let me write it again here. A square of xy equals delta if x equals y, 0 if x is adjacent to y, and 1 otherwise. And this is entry-wise, but if we write it as a matrix equation, this identity is the same as saying a squared equals. So in the first part, we have what happens on the diagonal. So it's delta. So that's the same as delta times identity plus second branch is 0 when x is adjacent to y, but those entries are the ones of the adjacency matrix. So that's 0 times a plus 1 times the entries corresponding to the complement of the graph, and the positions x, y, where x is not equal to y and x is not adjacent to y. And the matrix that takes care of these entries is the matrix of the complement of the graph, and it's all one matrix minus identity. So this kills off the 0 on the diagonal and it leaves 1 everywhere else. And then you go to the complement by taking off the adjacency matrix. So what we proved is this matrix identity, that the square of the adjacency matrix equals the expression on the right. And if we simplify it, what do we get? We get delta times identity plus j minus identity minus a. And if we rearrange it a little bit, moving things to the left-hand side, we end up with a squared plus a minus delta minus 1 times identity equals the all one matrix. Okay, all right. Now, how can we use this fact? Well, we can go after the eigenvalues and the multiplicities of the matrix A. So we already know that. So we know that A times the all one vector equals delta times the all one vector, and delta has multiplicity 1. Okay. So now let's consider another eigenvalue. So let's say AU equals lambda U. U is a vector that is non-zero. And lambda, because delta is multiplicity 1, we can say lambda is not delta. And we can assume that U is in the orthogonal complement of the all one vector. So U is perpendicular to the all one vector. Okay. So what can we say about this lambda? Well, we combine this fact with the equation above. So what we do is from the equation above, we multiply both sides by U, and we get that a squared plus a minus delta minus 1 identity times U equals j times U. Now, from here, we get that lambda squared plus lambda minus delta minus 1 times U equals, and here we use the fact that U is perpendicular to the all one vector, and that gives us a 0 vector here. And now, because U is not 0, that means that the expression in front of it must be 0. So lambda must satisfy this equation. Lambda squared plus lambda minus delta minus 1 must be equal to 0. Okay. So what we prove is that if lambda, which is not delta, is an eigenvalue of A, then lambda squared plus lambda minus delta minus 1 equals 0. Okay. Now that's a quadratic. So let's see what are the possibilities there. So if we look at lambda squared plus lambda minus delta minus 1 equals 0, well, here I use a bad notation because I have a delta and I'm not going to use the discriminant for the matrix, but for the equation, but it's easy for you to figure out that lambda 1, 2. So there are two possibilities. So, you know, lambda could equal, let's denote the first one by theta, and it's minus 1 plus square root of the discriminant, which is 4 delta minus 3 over 2. The discriminant is positive as delta is greater or equal to 2. And the other one is minus 1 minus 4 delta minus 3 over 2. So these are the possibilities. So, okay, what we showed is that if lambda is an eigenvalue, then lambda could be one of these two. Now, what we're saying is that A has eigenvalue delta with multiplicity 1, and at most 2 other eigenvalues. Okay. Now we claim that this at most is actually exactly 2 other eigenvalues. And the way we do that is that if A has eigenvalue delta and just 1 other eigenvalue, and 1 other eigenvalue, then I claim that the graph actually, then gamma has to be the complete graph k delta plus 1, but this one, which has diameter 1, contradiction with our assumption that diameter is 2, or delta t equals 2. So how, so I will prove this, this assertion here. Okay, how do you prove that? Well, if you have just 1 other eigenvalue, we know that A times the all-1 vector is delta times the all-1 vector. So that implies that anything perpendicular, so anything perpendicular on the all-1 vector is going to be an eigenvector for the other eigenvalue. So we get that AU equals lambda U for this other eigenvalue for any U. Okay, and then I can take U, for example, something of this form. I'll just do it for put a 1 in the first position, minus 1 in the second position, and 0 everywhere else. But you can do this for any I and j in the graph. So clearly U is perpendicular to the all-1 vector. And then what do I get when I calculate AU? AU is A times 1 minus 1, 0 everywhere. And so that's the difference between the column 1 in the graph, the column 1 of the adjacency matrix. So this is column 1 of A, which looks like what? I have a 0 here, and I have some entries somewhere else, minus column 2 in A, which is I have a 0 in the second position and various other entries. Okay, so this is AU. So this, the difference of these two vectors has to equal lambda times U, which is lambda in the first position minus lambda in the second position and 0 everywhere else. So this expression equals lambda minus lambda and 0 everywhere. Okay. So now what can we deduce from here? Well, the only way you have a lambda appearing here is that it must come from this entry here. So it's minus star of that entry. And similarly, the only way you have a minus lambda in the second position, it must come from the second entry in the first vector. And when you unpack these things, it follows that lambda must be equal to minus 1, and actually 1, the vertex 1 must be adjacent to the vertex 2 in the graph. But I can do the same argument for the difference of any two canonical vectors, EI and EJ, with I different from J. And this will give me that I is adjacent to J for any I different from J, and that would lead to the graph being the complete graph. So I hope this is clear. And again, what we're proving here is that the adjacency matrix of our graph, gamma, has actually 3 distinct eigenvalues. Delta and both theta and tau that are listed on the top are going to appear as eigenvalues. I mean, we could have seen this in a different way, but just in case there are questions, I think it explains it fairly well. Now, okay, so what do we have? So A has eigenvalue delta with multiplicity 1. And then we'll have this theta with some multiplicity m theta. And we'll have tau with some multiplicity m tau. And that's it. Those are our eigenvalues. And as before, theta is minus 1 plus square root of 4 delta minus 3 over 2. And tau is minus 1 minus square root of 4 delta minus 3 over 2. It's pretty easy to see that theta is positive and tau is negative. Okay. Now, so the goal here is to go after the multiplicities and try to say something about these multiplicities. Well, because the matrix is symmetric, we know that 1 plus m theta plus m tau equals the dimension of the matrix, which is delta squared plus 1. So that gives us one equation. M theta plus m tau must equal delta squared. Okay. And we can get another equation involving this multiplicities by looking at the trace of the adjacency matrix. That has to be 0, but it's the sum of the eigenvalues, including their multiplicity. So it's delta times 1, multiplicity first, 1 times delta, plus m theta times theta, plus m tau times tau. And if you unpack this, we get something, well, I'll change the order again here. Theta times m theta plus tau times m tau equals minus delta. Okay. Okay. So you have two equations. Now we have two cases of our proof. So okay. The case one, okay, case one is, so theta and tau are roots of this solutions of this equation x squared. So the polynomial that they are roots of is x squared plus x minus delta minus 1. This is the case when this is irreducible over rationals. Okay, that's case one. So what does that mean? It means that theta and tau are irrational numbers. Okay, and I claim that in this situation, the multiplicity m theta and m tau must be equal. Now, this is true in a more general setting, but let me give you the proof, you know, from scratch here. So what we have is that theta and tau are irrational, but because they are roots, so theta tau are roots of x squared plus x minus delta minus 1, these polynomials x squared plus x minus 1 factors is x minus theta times x minus tau. And we know that theta plus tau must be equal to minus 1. Okay, they're both irrational, but their sum is minus 1. Now, how do I prove that the multiplicities are equal? Well, I take the equation above, theta m theta plus tau m tau equals minus delta, and I can do theta m theta. I add a tau m theta, and then I subtract a tau m theta plus tau m tau equals minus delta. Okay, so far so good. Now, let me erase here. The first two terms here, they become m theta times tau plus theta, which I know that it's minus 1. And these other two terms become plus tau times m tau minus m theta equals minus delta. Okay, so what do we have? On the right-hand side, we have an integer number. On the left-hand side, we have the sum of two expressions, but the first expression is m theta times minus 1, so that's also an integer. And we have a tau times m theta minus m tau. M theta minus m tau is an integer. But tau is not rational. So the only way this expression makes sense is if this coefficient in front of the irrational number is 0, and that implies that m theta minus m tau is 0, so the multiplicities are equal. Okay, so all this work to get this part. So what can we deduce of m theta equals m tau? Okay. Well, let's look at our equations. So we had that m theta plus m tau equals delta square, but that will give us that 2 times m theta equals delta square. Okay, so that's one part. And we had that theta m theta plus tau m tau was minus delta, but now they're equal, the multiplicities, so we can take m theta as a common factor, theta plus tau, and we end up with minus delta. And what do we get? We get minus m theta equals minus delta, so m theta equals delta. And so we can take this and we can plug it in there. And what we get is that 2 times delta equals delta square, and delta is at least 2, so we get delta equals 2. So if we get delta equals 2, the diameter d was 2, so we're looking for, in this situation, we're looking for a 2 regular graph with 2 square plus 1, 5 vertices. And what can that be? It's just a cycle C5. So in this case, we get that gamma is C5. So that takes care of one part. Now, case 2 is when this polynomial, x squared plus x minus delta minus 1, is reducible, Q. So we have that x minus theta, x minus tau, equals polynomial, and theta and tau are rational. And I'll leave it as an exercise for you to prove that in this situation, actually, theta and tau, you can prove that there are integers. It's not too difficult. And so what do we get from here? Well, we're almost done. So I have that theta, which was minus 1 plus square root of 4 delta minus 3 over 2 is an integer. So it must be that the square root of 4 delta minus 3 must be an integer. And so it must be 4 delta minus 3 must be a perfect square. But because 4 delta minus 3 is odd, this has to be a perfect square of an odd number. So for some t, let's say t non-negative. Okay. So from here, what do we get? We get that, so square root of 4 delta minus 3 is 2t plus 1. And so theta, when we calculate it, is going to be minus 1 plus 2t plus 1 over 2 will equal this t, and tau is minus 1 minus 2t minus 1 over 2 is minus t minus 1. Okay, so all the eigenvalues are integers in this case. And now we just have to do a little bit more work. So we have the multiplicity add up to delta square, and we also have this other equation involving them. And now we just, from here, I will, if it as an exercise, it's not very difficult to get our hands on each of these two parameters, and we can prove that m theta equals tau delta square plus delta divided by tau minus theta. You just multiply one of these, the first equation, by tau, and you subtract them. And then if you want to get m tau, you multiply the first equation by theta, and you subtract them. So you get theta square divided by theta minus tau. Okay. And now once you get these formulas, these numbers must be integers, and so must be its difference. So when you do the difference between m tau minus m theta, that will equal, so at the bottom we'll have theta minus tau, and it will equal minus delta square plus 2 delta on the top. And this comes from the fact that the sum of tau, theta and tau is -1. So, okay, so we did all this work. The difference between the multiplicities must be an integer number. So therefore, this number here must be an integer. So what we have is that delta square minus 2 delta divided by theta minus tau must be an integer. But now theta was t, tau was minus t minus 1, so their difference is 2t plus 1. So that's at the denominator. Now what was delta? Well, delta, we have to pick it up from one of these equations. You have it from here. We have 4 delta minus 3 equals 2t plus 1 square. So 4 delta minus 3 equals 4t squared plus 4t plus 1. You move the 3 to the other side and divide by 4. So delta is t squared plus t plus 1. Okay. So what we have is that 2t plus 1, which is this part of the denominator, must divide delta square minus 2 delta, which is the same as delta times delta minus 2, and that's the same as t squared plus t plus 1 times t squared plus t minus 1. Now this is equivalent to 2t plus 1 dividing the same expression but with a 16 in front, and I'll show you in a second why we put 16. And with 16 in front, this is the same. One of the one factor of 4 from 16 goes to the first part. So we get 4t squared plus 4t plus 4. And the other one goes to the second part, 4t squared plus 4t minus 4. And now it's easier for us to peel off factors of 2t plus 1. So this first quadratic, you can write it as follows. You take 2t as a common factor times 2t plus 1. So we took care of the 4t squared, and now we have a 2t left, plus another 2t plus 1, and we have a 3 left from the 4. And this second quadratic, we do the same thing. It's 2t times 2t plus 1, plus 2t plus 1, and we have a minus 5. Okay. So what do we have? We have that 2t plus 1 must divide this whole product here, but we have factors of 2t plus 1 in almost all places. So in order for that to happen, we must have that 2t plus 1 must divide what is left over from here times what is left over from here, which is minus 15. So it might as well be 15. So 2t plus 1 divides 15. So that implies that 2t plus 1 can equal what? It can be 1, 2t plus 1 can be 3, 2t plus 1 can be 5, and 2t plus 1 can be 15. So what does it mean? This is t equals 0. This is t equals 1. This is t equals 2. And this is t equals 7. Okay. But what was delta? Delta was t squared plus t plus 1. So when t equals 0, we get the delta equals to 1, which is not interesting to us. When t equals 1, we get delta equals 3. When t equals 2, we get 4 plus 2 plus 1, it's 7. When t equals 7, we get 49 plus 7 plus 1, you get delta equals 57. That's the proof of the first part. Now, what happens for in each of these cases? So for delta equals 3, we have the this is a result, so one has to prove it, but the Peterson graph is the only graph that attains equality. So the Peterson graph is unique and it has delta squared plus 1, 10 vertices, and diameter 2. And when delta equals 7, I will talk to you about this in the next lecture. There is a graph, as I call Hoffman-Singleton graph, which is 7 regular, has 50 vertices, and diameter 2. So we'll do that next class. And when delta equals 57, it's not known if such a graph exists or not.